Observational, measured tone. For decades, access to orbit has been governed by one mathematical absolute, the Tsiolkovsky-Lockett equation. In order to lift a payload into space, a launch vehicle must carry the weight of the unburned fuel required to push it there. This breakdown shows the consequences of that math. To reach orbit, a typical launch vehicle dedicates approximately 85% of its entire mass to propellant. Structural components take up another 13%, leaving a mere 2% for the actual scientific instruments or human crew. Every gram of that remaining 2% requires dozens of grams of highly volatile, expensive liquid fuel to get off the ground. This paradigm restricts space commercialization to towering, explosive silos that require massive, complex infrastructure to maintain. To move past this bottleneck, a radical faction of aerospace engineers is looking past volatile chemistry. They are replacing explosive reactions with raw, mechanical kinetic energy. Medieval siege engineers perfected the mechanical blueprint for bypassing the rocket equation 8 centuries ago. The counterweight trebuchet operates on the conservation of mechanical energy. By raising a massive stone-filled box, the system stores gravitational potential energy. When released, that dropping weight applies a massive torque to the primary pivot, generating high angular velocity as the long throwing arm swings upward. The brilliance is the flexible sling. Acting as a secondary pivot, it creates a coupled dynamical system. As the beam rotates, the payload whips outward under centripetal acceleration. This extended radius moves the sling substantially faster than the solid beam. This precise manipulation of angular velocity manages those centripetal forces up to the millisecond the launch angle is reached. It multiplies kinetic transfer efficiency up to 83%, providing the mathematical template for 21st century orbital accelerators. Before translating rotational physics to modern space launch, engineers spent decades trying to scale linear acceleration. Back in the 1960s, Project HARP attempted to weaponize gravity and explosive propellants for suborbital research using massive naval artillery. Led by Dr. Gerald Bull, the program utilized an unprecedented 118-foot barrel. To survive the violent internal combustion of the cannon, Bull engineered the martlet, a slender, aerodynamic dart. The martlet was encased inside a machined wooden casing known as a sabot. The sabot acted as a pneumatic piston, creating an airtight seal to absorb the combustive energy of the powder charges as it traveled up the tube, discarding after it cleared the muzzle. The linear approach worked for suborbital research. In November 1966, a 16-inch HARP cannon hurled a payload 180 kilometers into the sky, successfully pushing well past the Kármán line into outer space. But Project HARP also illuminated a rigid physical wall. Explosive propellants apply their force in a shockwave that lasts only a fraction of a second, subjecting the payload to 25,000 Gs. Reaching orbit in a straight line requires either an infinitely long barrel or an instantaneous acceleration force that crushes modern electronics. To solve the linear limit, modern aerospace companies abandoned the straight barrel entirely. They returned to rotational mechanics to stretch the acceleration period out over hours instead of milliseconds. The physical scale of a modern mass accelerator is staggering. Orbital designs rely on a 100-meter-wide centrifuge designed to release a payload at Mach 6. To hit 4,700 miles per hour, the centrifuge spins at roughly 450 RPM. The mechanical consequence of this speed is that the payload experiences 10,000 Gs of centrifugal acceleration. Under these extreme conditions, a 10-ton launch vehicle pulls outward with 100,000 tons of force against the tether holding it. If that tether were made of traditional metals like titanium or high-strength steel, the complex von Mises stress created by the changing gravitational load vector would cause it to undergo plastic deformation and tear itself apart. Surviving those loads requires a breakthrough in material science. Engineers rely on aerospace-grade carbon fiber, specifically ultra-high tensile variants like Toray T1000G. With a tensile strength of over 6 gigapascals, it provides the ductility required to survive extreme cyclic fatigue without shattering. Because the spinning tether must support its own mass alongside the payload, it must be tapered, thickest at the central hub and thinnest at the tip. To prevent a wobble from shaking the 100-meter structure to pieces when the payload drops, A synchronous counterweight must be launched into a reinforced wall at the same millisecond. By enclosing this highly engineered composite tether in a near-space vacuum chamber, engineers attempt to scale the mechanics of medieval siege warfare into a functioning orbital launch system. The violence of a kinetic launch happens the moment the tether lets go. The vehicle instantly impacts thick sea-level air pressure at hypersonic speeds. The thermal physics of this transition are governed by the Fay-Riddell equation. Because the vehicle hits maximum velocity in the densest part of the atmosphere rather than the stratosphere, it generates a rapid spike in stagnation point heat flux. To survive this ascent, the launch vehicle operates as a disposable, heavily shielded aeroshell. It utilizes acute aerodynamic geometry to trade initial kinetic energy for altitude, rapidly coasting upward until the atmosphere thins and the charred casing can be discarded. Surviving the launch tube requires treating the lower atmosphere as a dense, physical wall of plasma. Even if the outer shell survives, the most persistent engineering hurdle is the payload inside. Under 10,000 Gs of rotational force, a 2-pound internal battery effectively weighs 20,000 pounds. Packing electronics into this environment forces a redesign. Liquid fuels are abandoned for solid rocket motors to prevent hydraulic pressure spikes, and standard aluminum chassis are replaced with shock-absorbing titanium and carbon composites to keep the internal structure from buckling under its own weight. Centrifuge flight tests have provided the real-world proof. Engineers spun commercial flight computers and sensors to 10,000 Gs, launching them tens of thousands of feet in the air and recovering them intact. Combining medieval kinematic principles with modern composite engineering has reduced the dependency on massive first-stage chemical boosters. While orbital insertion still requires a final rocket burn, the future of space access is increasingly being driven by pure mechanical force.